Number 7, the graph of a function is given to the right. Use separate graph paper and sketch the following. So we'll talk about these really quick. Adding 1 to a function, that's going to translate it up 1 unit. Okay, moving right along. Adding 1 to the input of our function is going to translate the graph left 1 unit. So when we get to that, we will translate that left 1 unit. Multiplying our function by -1 reflects our graph over the x-axis. So reflect over the x. And then we also have f of -x multiplying our inputs by -1, which will correspond to reflection over the y-axis. And last but not least, 2 times our function vertically stretches our graph. But to see exactly what to or how to draw these, you really just use the ordered pairs that are given to you. So for f of x equals f of x plus 1, all we're going to do is take the outputs and then add 1 to them. So here's the ordered pair -4, -2. So add 1 to the output. -4 now outputs -1 for this new function that we don't actually have a rule for, but its graph would be shifted up 1. Likewise, here's -2, -2 shifted up 1, 0, 1 shifts up 1, 3, 1 shifts up 1, and last 4, 0 shifts up 1. We can go back and connect these with a smooth curve, make it look nice and congruent to the original graph. And that's it. Number 2, f of x plus 1. Let's see if I can get a new graph here. Alright, just erase, oops, there it is. So if I look at adding 1 to our inputs, I actually need to add another little tick mark over here for -5. Why? Going back to this original point, which is -4, -2, adding 1 is actually going to translate our graph left 1 unit. So -4, -2 now becomes -5, -2. -2 translates our graph here. This one translate, and I'll connect these right now. Move this one, left 1, this point, left 1. Connect those. And last 4, 0 becomes 3, 0. There we go. So that's the graph of f of x plus 1. Alright, negative f of x. So we still have this ordered pair, -4, -2. I kind of like starting here. This will ultimately be your x-axis reflection, but if we literally do what we kind of know, take the opposite of the input, the output here. So -2 becomes +2, and again right here, connect those now. We have 0, 1 now becomes 0, -1, and 3, 1 becomes 3, -1, and 4, 0. Well, if you take the opposite of the output there, 0, still 0. So there we go. One thing to notice is that zeros never change their position under dilations. They always remain locked in place, if you will. These other points kind of end up in different spots, but the zeros stay where they are. Just a little side note there. Now let's go to f of -x. graph here. Okay. So if I look at this order pair, -4, -2, now I take the opposite of x. So this becomes 4, -2. -2, -2 becomes +2, -2. 0, 1, opposite of 0 stays 0. 3, 1 becomes -3, 1. And then we end at -4, 0. So connect those smoothly as possible. There we go. Good enough. Hopefully you get the point. And now you can see that that did correlate with a y-axis reflection. Last graph we need to do is 2 times f of x. So you have the graph up here. Here we go. Which color did I use? Green. So, oops. Computer's a little slow. So I'll go back to this point. -4, -2. Now we're doubling the output. So -4 now outputs -4. Double it down. -2 now outputs -4 as well. 1, 0, 1 now outputs 0, 2, 3, 1, 3, 2, and 4, 0. So again, under a dilation, our points stay the same, the zeros stay the same. I think I said that wrong earlier. But what I meant to say is if you multiply a function, the zeros are locked, even if it's by a negative value or a +2, whatever, the zeros remain. I probably should have sketched that a little better here. Alright, great. If you have any questions, please email me.